Okay. For any subspace of the vector space Rn, or directly by using this process we can generate an orthogonal or orthonormal basis for the vector space Rn generally. So it is explained in a theorem. Given a basis, let's say x1, x2, blah blah, xp, we have p vectors in the basis for a non-zero subspace or the vector space itself, W of Rn. This process is valid for the subspaces of Rn or itself. We cannot use this process, for example, for the set of all polynomials of degree at most n, for example. This is another vector space, or the set of double infinite sequences, and so on. The set of matrices, for example. This process is useful just for the subspace or the vector space Rn, real vector spaces. So we define the following vectors. V1, the new first vector V1 is the same as the first vector in the basis, which is x1. Okay, and V2 is defined by x2 minus x2 dot product V1 over V1 dot product V1. Namely, we find the dot products here, and it will be a scalar, and we multiply the vector V1, which is actually equal to x1, by this scalar, and we obtain the second vector. And the second one will be orthogonal to the first one, because this one is the orthogonal projection of x2 onto the x1, and by subtracting from x2 we obtain the orthogonal complement. Therefore V2 is orthogonal to V1. And also you can see clearly V2 dot product V1 is equal to V2 is equal to this one, and we distribute V1 onto the subtraction. So we write x2 minus x2 dot product V1 over V1 dot product V1 and dot product V1. Okay, and from here, namely, we see the inner product is equal to 0, which means that they are orthogonal. So we have x2, after distributing this thing into the parentheses, x2 dot product V1 minus x2 dot product V1 over V1 dot product V1, but here we have the same thing here, V1 dot product V1, which means that we can simplify them. Therefore, just we have x2 dot product V1. Therefore, the subtraction will be 0, which means that V2 and V1 are orthogonal. And similarly, V3 is equal to X3. At the beginning, we have a basis and we don't know this is orthogonal basis or not. If you don't have an orthogonal basis for the subspace or vector space, we can generate an orthogonal basis by using the given one. If it is not orthogonal, how do we get an orthogonal basis? By using the Gram-Schmidt process. So x3 minus x3 dot product v1 over v1 dot product v1 minus, because we generate the third vector v3. Therefore, also we take the orthogonal projection of x3 onto v2. v2 over v2 dot product v2. So this one is a scalar. Dot product over dot product is a scalar. V2 is a vector, and here we have a scalar multiplication, which is again a vector. Okay, if you remember. And by following this way, lastly, the last vector VP, sorry, not X, is equal to XP minus XP dot product V1. Here we should write V1 over V1 dot product V1 minus XP dot product V2, the second vector, over V2 dot product V2. And until the previous vector Vp minus 1 minus XP dot product Vp minus 1 over Vp minus 1 dot product Vp minus 1. So we have p terms here, and all of them are orthogonal to each other. This is V3, and we see that V1, the set containing these vectors, is an orthogonal basis. Orthogonal basis for the subspace. At the beginning we have a basis actually, but it is not orthogonal. But by using this basis, we can generate an orthogonal basis, which make easier the calculations in the subspace or the vector space to obtain a lot of properties easily. Therefore, we find an orthogonal basis. After finding an orthogonal basis for the subspace, so to see the properties of the subspace easily, we can benefit from this basis. Because in addition, the sets spanned by the vectors given here, x1, x2, blah blah, xp, is equal to actually the set spanned by V1, V2, blah blah, VP. Therefore, we can take the set containing the vectors V1, V2, blah blah, VP as a basis for the subspace, and also it is an orthogonal basis. Namely, when we take any two vectors from here, for example V2 dot product V3, so it is equal to 0. They are orthogonal. The angle between them is 90 degree. Or you can take another pair. Let's say, for example, V4, V4, V7. So the inner product will be also 0. And if you remember, in high school or in the first year, always we use the coordinate system, x-axis, y-axis. Why it is useful? Because the angle between them is 90 degree. We have actually an orthogonal basis for r square, the two-dimensional coordinate system. And always we sketch the graphs of functions, or we do all operations according to this coordinate system. And to get this coordinate system, we need to find an orthogonal basis, also an orthonormal basis. Actually, it is created by the vectors E1 and E2. If you remember, E1 and E2 form a standard basis, and they are orthogonal. Namely, the angle between them is 90 degree. This is an orthogonal basis. Also, it is an orthonormal basis because the norms are equal to 1. The norm of E1 is equal to 1. The norm of E2 is also equal to 1. If the norms of vectors in the orthogonal basis are equal to 1, so we say that this is an orthonormal basis. Moreover, if the norm of every vector, let's say generally Vi, is equal to 1 for all I, which is between 1 and P, then the set V1, V2, blah blah, VP is called an orthonormal basis. Do you have any question? An orthonormal basis for the subspace of Rn, or directly for Rn if you have n vectors. Okay. Or we can generate also an orthonormal basis by finding the unit vector in the direction of the vectors v1, v2, blah blah, vp, if they are not unit vectors. Namely, we should obtain unit vectors for every vector in the basis to get an orthonormal basis. If they are not unit vectors, in other words, if the norms of them are not equal to 1, so we can generate vectors in the direction of these vectors whose norms are equal to 1 by using the formula, namely u1, for example, is equal to 1 over the norm of v1 times v1. This is the unit vector in the direction of v1. U2 is defined by 1 over V2, namely the norm of V2 times V2 and blah blah. The last one, UP, is 1 over VP times VP. Okay. So now directly we can say that U1, U2, blah blah, UP is an orthonormal basis. Is an orthonormal basis for the subspace. Okay. So to get first an orthogonal basis, just we calculate the vectors written here by using the formulas here. And then if you want to obtain an orthonormal basis, just you will find the unit vectors in the direction of the vectors in the orthogonal basis. And this process is called the Gram-Schmidt process, and it is more useful in applied science to get easy calculations for the vector space, to see the graphs of functions easily. We need to obtain an orthogonal or orthonormal basis, as you can see, for example, in R square, in R cube also, to find the volume or to define an integral, double integral, and so on. We have to obtain orthonormal basis to define easily. Otherwise, the calculations will not be easy. This will be very hard. Therefore, we should obtain an orthonormal basis to make easier the calculations in the vector space. For example, if you don't have any question so far, we can see an example to understand very well this topic. Let's write this example in the second page. So we have three vectors. X1 has the components 1, 1, 1, 1. X2 has the components 0, 1, 1, 1. X3 has the components 0, 0, 1, 1. So we see that x1, the set containing these vectors x1, x2, x3 is linearly independent. You can see yourselves. You can create a matrix by considering these vectors as columns. For example, this is the first column, second column, and third column. And you will find the echelon form, and you will see in every column you have pivot positions, which means that the columns are linearly independent, you know. Independent. And therefore, it is a basis for the subspace, for any subspace W, for the most easy subspace is the set spanned by them. Also, you can find another subspaces whose basis is the set given here. X1, X2, X3. Of R4, because the number of components, as you can see, are 4. Therefore, this is a subspace in R to the 4. So construct an orthogonal basis. For the subspace. Okay, just we will use the Gram-Schmidt process. According to the Gram-Schmidt process, Gram-Schmidt process. So V1 is equal to X1. V1 is equal to X1, namely the components for V1 are 1, 1, 1, 1. The second formula, V2, let's look at the formula. X2 minus the dot products times V1. X2 minus X2 dot product V1 over V1 dot product V1 times the vector V1. Okay, first let's find the dot products. X2 dot product V1. What is V1? V1 is equal to X1, namely we take the dot product of X2 and X1. From here, 1 times 0 is equal to 0, plus 1 times 1 is equal to 1, 1 times 1 is equal to 1, 1 times 1 is equal to 1, respectively. We multiply the components, corresponding components, and the dot product will be 3. And also we need to find the dot product of V1 by itself. So it is equal to, namely V1 is equal to X1, the dot product is equal to 1 plus 1 plus 1 plus 1, which is equal to 4. Therefore, it is equal to X2 minus, namely 0, 1, 1, 1, minus, first we should write the scalar. So this the numerator is equal to 3 and the denominator is equal to 4 times the vector V1. What is V1? Which is, this is equal to X1. So we have 1, 1, 1, 1. Therefore, V2 is equal to, so 0 minus 3 over 4 times 1 becomes minus 3 over 4. 1 minus 3 over 4, because 3 over 4 times 1 is equal to 3 over 4. 1 minus 3 over 4 is equal to 1 over 4. And 1 minus 3 over 4 for the third component is again 1 over 4, and the last component is also 1 over 4. That's it. This is the second vector. And to make easier the calculation, we can take any multiple of this vector. Since we have fractional numbers here, like 3 over 4, 1 over 4, 1 over 4, to make easier the calculation, to facilitate the calculation, we can take 4 times V2 to get rid of the fractional numbers. So we can take V2 prime as minus 3, 1, 1, 1. This is more easy than the previous one. We don't have any fractional numbers, as you can see. We have integers for the components. Therefore, we take this to get an easy calculation for the next vector. Since we have 3 vectors here, so we should find 3 orthogonal vectors to each other to get an orthogonal basis. So the third one, V3, is equal to, from the Gram-Schmidt process, x3 minus x3 inner product V1 over V1 inner product V1 times V1 minus, this is the third vector, we have 2 vectors from here. Therefore, after finding the orthogonal projection of x3 onto V1, also we find the orthogonal projection of x3 onto V2. Dot product V2, V2. So to find the components of V3, we should calculate this operation. Therefore, we should find the inner products written here. Okay, x3, x3 has the component 0, 0, 1, 1. Okay, 0, 0, 1, 1 minus x3 dot product V1. V1 is equal to x1. So from here we take the dot product of x3 and V1. 0 times 1 is equal to 0. 0 times 1 is equal to 0. 1 times 1 is equal to 1. 1 times 1 is equal to 1. So we have 2 for the numerator over V1 dot product V1. So this is equal to 4 times the vector V1. V1 is equal to x1, so we write 1, 1, 1, 1 minus x3 dot product V2. Namely, actually we take this one to get an easy calculation. Therefore, we write V2 prime. X3 dot product V2. So the first 2 components are 0. Therefore, we just interest in the last 2 components, 1, 1. 1 times 1 over 4 is equal to 1 over 4. 1 times 1 over 4 is equal to 1 over 4. Addition of them will be equal to 1 over 2 over, we take the dot product of V2 prime by itself. So we have 9 plus 1 plus 1 plus 1, 10, 12. 12 dot product and V2 prime.
Hocam prime'ı kullanmamız gerekmiyor muydu? Siz V2'yi kullandınız pay kısmında.
Can you repeat again?
V2 prime kullanmadınız da V2 kullandınız pay kısmını yazar.
Okay, I understood. From here, okay, we have minus 1 times minus 1 times 1. Okay, I see. So the last components is 1 and 1. 1 times 1 is equal to 1. 1 times 1 is equal to 1. So this is equal to 2. Okay. I think now this is true. Minus 3, 1, 1, 1. If there is no mistake here, we obtain 0, 0, 1, 1 minus 1 over 2, 1 over 2, 1 over 2, 1 over 2 minus, so we have 1 over 6 becomes minus 1 over 2 for the first one, 1 over 6 times minus 3 minus 1 over 2, 1 over 6, 1 over 6, 1 over 6. And from here we should obtain actually minus 1 over 2 plus 1 over 2 becomes minus 1 over 2 plus 1 over 2 becomes 0. Okay, the first component. Minus 1 over 2 plus 1 over 2 is 0. Minus 1 over 2 minus 1 over 6 becomes minus 2 over 3. Minus 2 over 3. Minus 2 over 3. 1 minus minus 2 over 3 becomes 1 over 3. 1 over 3. And the last one is also equal to 1 over 3. So this is V3. So that's it. V1 has the components 1, 1, 1, 1. V2 has the components actually V2 prime minus 3, 1, 1, 1. V3 has the components 0, minus 2 over 3, 1 over 3, 1 over 3. Or like the second vector V2, to get rid of the fractional numbers, you can multiply this vector by 3 to get an easy vector. And you will see, for example, let's see, V1 inner product V2 prime should be 0. Let's see. 1 minus 3 is equal to minus 3. 1 times 1 is equal to 1. 1 times 1 is equal to 1. 1 times 1 is equal to 1. As you can see, this is equal to 0. Namely, V1 and V2 prime is orthogonal to each other. Similarly, let's see, V1 dot product V3 should be equal to 0. 0 plus minus 2 over 3. 1 times 1 over 3 plus 1 over 3 plus 1 over 3. So this is equal to 0, which is very interesting. As you can see, by using the Gram-Schmidt process, we obtain vectors which are orthogonal to each other. So we say that by using the Gram-Schmidt process, we obtain an orthogonal basis, namely V1, V2, V3 creates an orthogonal basis. It is an orthogonal basis. How can we obtain an orthonormal basis for the subspace W? So just we write U1 is 1 over the norm of V1 What is the norm of V1? Or let's write here again directly. The norm of V1 is the square root of the sum of the squares of the components. 1 squared is equal to 1, 1 squared is equal to 1, 1 squared is equal to 1, 1 squared is equal to 1. The sum of them will be 4. V1 and U2 is equal to 1 over the norm, namely the square root of 9 plus 1 plus 1 plus 1 becomes 12. By the way, this is actually 2. Square root of 4 is 2. This is U2, V2 prime, and U3 is equal to 1 over square root of 4 over 9, 1 over 9, 1 over 9. We have 6 over 9 becomes 2 over 3 times V3. Namely, you will multiply the vector V3 by the scalar written here. So you obtain an orthonormal basis. U1, U2, U3 is an orthonormal basis. For the subspace. Okay? Do you have any questions so far? Maybe I can ask a question in the final like this one. By using the Gram-Schmidt process, you will obtain an orthogonal basis. Just you will use the formulas written here. And that's it. This is the Gram-Schmidt process, and you can solve more questions from the textbook to practice. And the last thing in this section is to explain the QR factorization. You know, in the previous sections, in the chapter 2, you know a factorization which is called LU factorization. When we have a matrix A, n by n, so this can be factorized as L times U. You know, L is the lower triangular matrix, if you remember. Triangular matrix. What is U? Can you say? Do you remember?
Upper triangular matrix.
Other name? Yes, this is upper triangular matrix, but we have a name. Actually, we know always. We obtained in the chapter 1.
Echelon.
Yes. Echelon form. And you know this procedure to get the factors of the matrix A, which are the matrices L and U, by applying the matrix multiplication for them, you can obtain A. And this is useful in applied science to find, for example, the eigenvalues or another properties of this matrix, or to solve any problem related to this matrix. And another useful factorization is called the QR factorization. Namely, when we have a matrix A, which is m by n, so this is written as Q times R. Q and R matrices, where Q, the matrix Q, is an m by n matrix, whose columns form an orthonormal basis, for the column space of the matrix A, for the column space, okay, for the column space of the matrix A, and R is a square matrix which is m by n, Q is m by n matrix, R, the second matrix, is n by n square matrix, n by n, upper triangular matrix. In the LU factorization, we obtain lower triangular matrix, but here we have upper triangular matrix. With positive entries. On its diagonal. On the diagonal of this matrix, we have positive entries always. And how can we obtain the entries? So R is obtained as the transpose of Q times the matrix A. By multiplying them, we obtain the second matrix. So this is obtained actually since you know A is equal to Q times R, and from here by multiplying this equality by the inverse of the matrix Q, namely the inverse of Q times A, and Q is an invertible matrix because the columns are orthogonal vectors which are linearly independent. Therefore, we can obtain the inverse of Q. This is equal to R because the inverse of Q times Q is equal to the identity matrix. And identity matrix is not written in the matrix multiplication, does not affect the multiplication. And since Q is an orthogonal basis, and we know from the second section of this chapter, namely 6.2, when we have an orthogonal matrix like Q, because the columns are orthogonal to each other, the columns of this matrix are orthogonal to each other, so the inverse of Q becomes its transpose, namely without doing any operation that we have learned from the previous chapters, like the chapter 3 or chapter 2, just by taking the transpose of this matrix. How you can obtain the transpose? The rows become the columns for the transpose. Therefore, we obtain this formula, namely R is equal to, instead of the inverse, we write the transpose of Q times A. So this is called QR factorization for any matrix in the vector space. As an example, if we consider the previous example, we obtain actually, if we say the matrix A has the columns x1, x1, x2, x3. In other words, 1, 1, 1, 1. The other, I guess 0, 1, 1, 1. And the last one is 0, 0, 1, 1. So find QR factorization. Q times R for this matrix. QR factorization. So in the previous example, we obtained the orthogonal basis for orthogonal vectors corresponding to x1, x2, x3 actually. They are v1, v2, and v3. Also, we obtain orthonormal vectors, which are u1, u2, and u3. So Q will be actually u1, u2, u3. So we see that actually x1, x2, and x3 are linearly independent. Therefore, we obtain v1, v2, v3, which are orthogonal to each other for the column space of the matrix A actually, because a basis for the column space has the vectors x1, x2, x3, and the corresponding orthogonal basis will be v1, v2, v3, and the corresponding orthonormal basis will be u1, u2, u3. So let's write u1 1 over 2 times v1, 1 over 2 times v1, namely 1 over 2, 1 over 2, 1 over 2, 1 over 2. And u2 is square root of 3 over 2, square root of 3 over 2. And when we look at the components, minus 3, 1, 1, 1. Minus 3 times square root of 3 over 2, 1 times, namely square root of 3 over 2.
It's U3.
Yes, U3. U?
It's U3.
U2. U2. This is U3, yes, U2. 1 over square root of, namely square root of 2, 1 over square root of 2 times 1 over 2 times square root of 3 v2 prime minus 3 times this one. Yes, this is true. Thank you.
You're welcome.
Minus 3 times 2 over square root of 3. And the second component, 1, 1, 1. 1 over 2 times square root of 3. 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 And the last column is u3, square root of 3 over 2, actually v3. So we have 0, square root of 3 over 2 times 2 over 3 minus 2 over 3. You can arrange this yourselves. Just I try to explain an example to see. 1 over 3, 1 over 3, 1 over 3, 1 over 3, square root of 3 over 2, 1 over 3, square root of 3 over 2, 1 over 3. Okay, this is the matrix Q, and of course you can obtain R. What is the transpose of this one? So this is actually 1 over 2, 1 over 2, 1 over 2, 1 over 2. The first column becomes the row, as you can see. for the transpose of Q minus square root of 3 over 2, this one, 1 over 2 square root of 3, and so on. And the last column, 0. I guess this is minus square root of 2 over square root of 3, and 1 over square root of 6. Yes. And this one is also 1 over square root of 6. Times the matrix A. 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1. And after the multiplication, you can obtain R. Okay? This is called the QR factorization, which is also useful in applied science. Okay, from the section 6.4, you should know the Gram-Schmidt process written here. And also you should know the QR factorization. QR factorization. This is the section 6.4. Do you have any question about that? Did you understand? I hope there is no problem. Okay, that's it. This is the section 6.4. So I can take your questions.